Evan, can you please stop sharing the screen for one moment? All right, yeah. So after we start, after that you can start sharing. טוב, אנחנו נתחיל. Evan, we can start right now, or we'll start in Hebrew. שלום לכולם. אני שמח לפתוח שוב את הרצאות ההשערה שאנחנו עורכים לחברי הבורסה, לחברי וחברות הבורסה, במגוון רחב של נושאים. כל ההרצאות שלנו כמובן אנחנו קוראים לכם לבוא ולהשתתף ולשמוע ולהקשיב ולהשאיר את הידע, לאחר מכן אנחנו שמים אותם באתר הבורסה, תמיד אפשר ליהנות מהם גם בהמשך. הפעם אנחנו שמחים מאוד מאוד לארח את דוקטור אוון סמית, מצוות המחקר של GIA בניו יורק, והפעם הנושא הוא תעשיית היהלומים הטבעיים. כשזה בא מנציג של ה-GIA, אז זה באמת מרתק לשמוע את הצד שלו כאיש מקצוע בתחום הזה, ובנוסף את המהלכים השונים שנעשו לאורך השנים בתחום הזה של היהלומים הטבעיים, ומה בכלל הופך יהלומים טבעיים לכאלה מיוחדים במשך מיליוני שנים. אז אני מאחל לכם האזנה נעימה. שוב, אני חוזר ואומר שההרצאה מוקלטת, וכמובן שאם יהיו שאלות בהמשך, ניתן להעביר אותם בצ'אט, אם זה בעברית ואם זה באנגלית, אני מנסה להעלות אותם מולו, על מנת שהוא יוכל לענות על השאלות. אני אעבור דקה אחת לאנגלית. All right, hello Evan. We are very honored to host you, Dr. Owen Smith of the GIA New York research team, with the lecture that will deal with the natural diamond industry, the various moves that have been made over the years in this field, and what in general makes natural diamonds such special for millions of years. So Evan, we are really very honored to host you here, and the stage is yours.
Well, thank you very much. I'm very pleased to be here with you. I was really happy when I got the invitation to speak to this group. And I'm a little bit of a different kind of person than you might be expecting to hear from GIA, because I'm not really dealing at the core of gems and jewelry or diamond grading. My background is as an earth scientist, so I deal with the geology of diamonds. So when I look at diamonds, most of what I'm doing is looking at diamonds as a natural material to try to understand how they form and what we can learn from them in terms of our understanding of the earth. So some of the things that I've found in the past few years have turned out to be interesting, not just to me, but I think to a broader audience. And that's what I'd like to talk about today. So let me just pull up my slides here. So what I'd like to talk about is sort of natural diamonds and what makes them special, how they form and what makes them special. And I think this is kind of a relevant topic right now because of the increasing prevalence of lab-grown diamonds in the marketplace, people are starting to wonder, you know, are lab-grown diamonds equivalent or comparable to natural diamonds? For many, many years, natural diamonds have sort of spoken for themselves. They've needed no introduction. They've needed no justification. They've just been a beautiful gemstone that's been considered sort of the ultimate gemstone for many. So I think now is a good time to sort of revisit some of the things that make natural diamond special in terms of sort of viewing them as a new way to appreciate diamonds in comparison to lab-grown diamonds. So what is it that makes diamonds special? I think when you ask a lot of people, they talk about the properties, the physical properties of diamonds. For instance, its hardness. It's extremely hard. It's harder than any other natural material that we know of. And it's a beautiful gem material. It can sparkle. It has this scintillation and fire that's appealing to just about everybody. It's relatively rare. It's a valuable material. And it has this symbolism that we attach to it. It's something that we exchange at special occasions as a gesture of love or commitment, or celebration. So those are sort of the things that I think most people would associate with diamond. But where I come in from looking at diamonds from a sort of geological aspect, I think about the story behind the diamond. And I think this is something that adds to the discussion surrounding diamonds, and especially now provides perhaps a new context for people to appreciate natural diamonds. Now, one of the things people can appreciate that's pretty tangible about natural diamonds is where they come from. So I just wanted to take a moment and mention the GIA Diamond Origin Report that started last year. And this is a service that allows a polished diamond to have a certificate that states what country the diamond came from. And this is only possible if GIA has analyzed the rough before it's gone on to be polished. So the idea is that a rough diamond comes into GIA for the GIA rough analysis service. And then we have this record of the diamond and sort of its fingerprint. And then after it gets cut and polished, we can match up that cut and polished diamond with the rough. And this sort of assumes that we have a control on the rough and where it came from. Quite often when rough diamonds are mined and pulled from the earth, there are people there recording it. They know where it came from. The miners know what mine it comes from. So as long as there's this chain of custody from the mine site, we can be confident about where the rough comes from. And the idea with the Diamond Origin Report is to take that information that we know about this rough diamond. For instance, this is a real rough diamond shown on the top right here. And we know that it's from South Africa, from the mining company. And we can now transfer that information from the rough to the polished diamond. And now, because of this continuity, being able to match up the rough diamond with its cut and polished counterpart, we can give this information to the consumer and say, yeah, this diamond, we've tracked it and we know that it comes from, in this case, South Africa. And you can learn more about this on the GIA website shown here. And this is a real GIA report number if you want to check out what this report looks like. But I don't have a whole lot to do with that particular service. Again, I'm an earth scientist, and most of the time I'm looking at diamonds as a mineral, and I'm interested in what's trapped in them and what kinds of information they contain. So a mineral is anything that's made up of atoms and it has a definite chemical composition. And in the case of diamond, it's made up of carbon atoms, and they're arranged in a crystal structure that repeats. And in the case of diamond, it has this cubic crystal structure that's sort of shown here in this cartoon. And a mineral is naturally occurring. So diamonds are naturally occurring. And there are lots of minerals around us, and many of the gem materials that we're familiar with, like rubies and sapphires or emeralds, these are all minerals. And most minerals, including all of these gem materials, form naturally in the earth, but they form around us in the earth's crust. So at relatively shallow depths, maybe 1 or 2, maybe even 10 kilometers deep in the earth. So they're forming within the uppermost part of the earth, in the earth's crust. And this is very different from what the story is for diamonds. Diamonds form much, much deeper in the earth's mantle, typically at depths of 150 or 200 kilometers and even more. Now, if we sort of take that picture and zoom out a little bit, this is what I'm talking about. So most minerals that we know of form in the earth's crust, in this outermost layer, and the mantle is this middle layer of the earth stretching all the way down to about 2,900 kilometers, where we then intersect the core of the earth, which is iron and nickel. So this mantle of the earth is kind of an unusual place that we don't know a whole lot about it, but diamonds form in this region of the earth. So as I mentioned, diamonds form deep in the earth, beneath the crust, and most of them, maybe 99% of the diamonds we know of, form in the base of old and thick continents, up to about 200 kilometers deep. And very rarely, there are even diamonds that form deeper in the earth, deeper than about 200 kilometers, maybe even as deep as 1,000 kilometers or more. So these are the only natural materials we have that come from such a great depth in the earth. And that alone makes diamond a really exotic natural material. It's almost like the opposite of a meteorite coming from space. It's like this little crystal that comes from far beneath our feet, from this place that we can't go or see in any other way. So when I look at diamonds like this one, this is a 163 carat, huge, beautiful type 2 D color flawless diamond. I see it as a beautiful gemstone, but I also see it as this sort of exotic material that's come from very, very far beneath our feet. So if we sort of try to make a picture of what this looked like, so we've learned a lot from diamonds, but in particular from studying the inclusions in diamonds. And this is what we think diamond formation might look like. So here's a section, a cross section of the earth, and here's the earth's crust up here in beige, and then deeper down here, we've got a little diamond crystal that's starting to grow. And as it grows larger, perhaps it can envelop another grain of the surrounding rock. And this is what becomes an inclusion in the diamond crystal. And later, if we're lucky, I mean, the natural question is, how does this diamond actually make its way up to surface where we can mine it? And the answer to that question is, well, sometimes diamonds are swept up to surface in these special volcanic eruptions called kimberlites. So this is a volcanic eruption that has swept some material up to surface, including this diamond. And the diamonds we find at Earth's surface have all been carried up in volcanic eruptions like this. And then when we look at this diamond here, some diamonds like this, we have these inclusions trapped inside them. And this little piece of foreign material was trapped and preserved really well from these extreme depths in the earth. So diamonds contain inclusions, and these inclusions are physical samples of the deep earth. And that means that diamonds carry with them this valuable information from this place that we can't go or study in any other way. So from studying inclusions like the one in the cartoon there, we've learned that there are different kinds of diamonds, which is kind of surprising. 100 years ago, we didn't know that. We didn't even guess that, but now we know that there are multiple different ways diamonds can form. And the overarching theme for diamond formation is that diamonds form by carbon crystallizing out of a fluid. And it might look something like this. So down at the bottom here, I've got a slice of rock, and you can see there are some green minerals and some purple minerals. The purple is garnet, which sometimes you find it as an inclusion in diamonds. And in this rock, say we're 200 kilometers down beneath the Earth's surface, diamond formation might involve fluid percolating up into this rock along those grain boundaries. And this fluid sometimes can crystallize carbon. And in this case, we've got a larger diamond here that's actually trapped one of these purple grains. And this is a garnet inclusion in this diamond now. So this is how we've learned a lot of what we know about diamonds and how they grow. We know that there are different kinds of carbon-bearing fluids, so different kinds of fluid involved, and sometimes there are different kinds of rocks. So this slice of rock that I've shown here, this is just one kind, but there are other environments where diamonds can be forming, other host rocks, and in those cases, we would expect to see different kinds of inclusions trapped in the diamonds. So here's a couple examples of inclusions in some faceted diamonds. On the left here, we've got an orange garnet and a blue kyanite crystal. And on the right, this is a pink diamond, and in it, it has this little colorless crystal trapped here. And this is a mineral called olivine. And these are relatively common mineral inclusions, but these are little samples of the host rock where these diamonds grow. So these are like a little snapshot frozen in time that tell us what it looked like where this diamond was growing. So most of the diamonds that we have seen based on their inclusions, we interpret them as having formed in the base of old and thick continents. So here, this thicker part of the continent, we have these little black symbols here. These are diamonds that have formed at depths of 150 to 200 kilometers. And we would call these lithospheric diamonds. So this package of brown rocks here, that's called the lithosphere. And these are diamonds formed in the bottom of the lithosphere. So these are lithospheric diamonds. And in contrast to this, sometimes we see diamonds that look like they have inclusions that were trapped even deeper in the earth. And these are called sublithospheric diamonds, or sometimes we call them super deep diamonds. So very rarely we have diamonds that have actually formed as deep as 1,000 kilometers or more down in the earth, which is going maybe even beyond just kind of something interesting, but something that's truly special. Now, again, when we look at this diamond here, it turns out that this diamond actually does belong to that special category of super deep diamonds. And this is something that we've learned only in the last 4 years, that diamonds like this actually belong to this unusual category of super deep diamonds. Another thing that comes up in conversation is the age of diamonds. And quite often people say that diamonds formed 3 billion years ago. And for many diamonds, that's true. So if we put this on a little timeline here, we're going from the age of the Earth, which is about 4.5 billion years old. And some diamonds, especially from northern Canada, from the Acadie and Diavik diamond mines, these are some of the oldest diamonds that we know of, and they formed upwards of 3.5 billion years ago. So they're almost as old as the Earth itself. There are also some younger diamonds. For instance, the diamonds from the Argyle mine in Australia, those ones are a little bit younger, and this mine is known for its pink diamonds. And many of these diamonds are around 1.6 billion years old. There are even some diamonds that formed younger than this. For instance, in South Africa, from the Jagersfontein and Koffiefontein mines, some of these diamonds are not billions of years old, they're only millions of years old. Here, many of the diamonds are 90 million years old. And after this, you can see on this timeline, I've added the extinction of the dinosaurs, which was 65 million years ago. So people think of dinosaurs as being long away in the past, something that happened a long time ago. But most of the world's diamonds formed much, much longer ago than that. So what we've learned from diamonds, so far I've shown you that some diamonds, they're forming extraordinarily deep in the earth, and some diamonds are extremely old. And based on these two things together, diamonds are not just beautiful pieces of gemstone for jewelry purposes. Diamonds are really a scientifically valuable sample of the earth. And we've learned a lot about the earth from studying diamonds. So here's a picture of a diamond that made the cover of Science. This is a very well-respected, internationally renowned journal. And, you know, this was just 2016. So we're still learning a lot about diamonds on the scale of things that would be interesting to an international scientific audience. Some of the things that we've learned about from studying diamonds, we've studied continent formation, tectonic plate activity through time. We've learned about the deep carbon cycle, so the exchange of carbon from the surface of the Earth into the Earth's interior, and also vice versa, the exchange of carbon from inside the Earth into the Earth's atmosphere. We've learned about the movement of materials inside the Earth and about the composition of the Earth itself, what the Earth is made of. So I want to give you an example of some kind of a big idea that we've learned about from studying diamonds. So we've learned a lot about plate tectonics. Now, plate tectonics is a theory that emerged in the 1960s. The idea is that the surface of the Earth is made up of plates, and these plates have boundaries between them, and these rigid plates on the surface of the Earth can move around, and where they bump up against one another, this is where we have earthquakes. Now, this is what it looks like at the Earth's surface. We can see the Earth being divided up into plates. But if we look at this in cross-section, we can see that there's something much more interesting going on. So this is what these plates look like in cross-section. And there are two main kinds of plates. One, it would be the continents, the dry land where we live. And those plates are relatively stable. They just stay at the surface of the Earth. But oceanic plates, all these tectonic plates that are under the oceans, these are much more mobile, moving plates, and they're formed continuously inside the ocean at these mid-ocean ridges. And this material moves away from the ridges almost like a conveyor belt. And eventually, many of these plates actually get pushed down into the Earth in a process called subduction. So the tectonic plates under the Earth's oceans are all relatively young because they're continually being subducted or carried down into the Earth in this process called subduction. Now, we can see some evidence of this in diamonds, actually. So remember those mineral inclusions that I showed you earlier? Well, we had a garnet and a kyanite crystal that correspond to the rock type called eclogite. And eclogite is what you get when this oceanic crust material gets carried deep down into the Earth and is subjected to very high temperatures and pressures. Those rocks turn into something called eclogite, and that is what some of these diamonds have grown in. They've grown in this rock that we know used to be at the surface of the Earth at the bottom of the ocean. Another rock type I'm showing here is peridotite, and this is what we think makes up a lot of the interior of the Earth. So it makes up this beige material here underneath the continents, and it also makes up this orange and yellow material that's deeper down in the Earth. And we see this in some inclusions, for instance, that inclusion of an olivine. An olivine is a mineral trapped from this rock type that makes up much of the interior of the Earth. So here are those mineral inclusions again. We've got this garnet and kyanite that are growing. This is a diamond growing in this rock called eclogite, which used to be part of the ocean crust, we think. And then here's this olivine, which is a sample of this host rock called peridotite. So here's some more examples of some inclusions. Here's another orange garnet from eclogite and another kind of garnet that contains chrome. This is a purple or a reddish purple kind of garnet called a chrome-rich pyrope garnet, and this is from a peridotitic rock. And we've also got an example of this vibrant green, chrome-rich clinopyroxene, and this is, again, something that was trapped from a peridotite. Now, if we go back to this diagram here and talk about these two major kinds of diamonds, ones that are growing in eclogite and ones that are growing in peridotite, we can make a really interesting observation by adding in the factor of time here. So we know something about how old these diamonds are. I haven't mentioned anything about it in this presentation, but sometimes we can measure the age of diamonds by studying the inclusions. It's a destructive analysis. You have to break the diamond open and study its inclusions. Usually you're studying the sulfide inclusions, like iron and nickel sulfides trapped in the diamond. But the important thing that I want to tell you is that all of these eclogitic diamonds are younger than about 3 billion years, whereas some peridotitic diamonds formed before 3 billion years, upwards of, we said, 3.5 billion years old. So that tells us that within the record of diamonds, we don't see any of these eclogitic diamonds before 3 billion years. So that probably means that this whole process of subduction wasn't happening before 3 billion years ago. So there was a period of Earth's geological history where something else was happening to sort of have the surface of the Earth interacting with the interior of the Earth, but it didn't look like this picture. We don't know what it looked like. So this process of subduction ocean crust, this crust appears in the diamond record only after 3 billion years. So, and this agrees with other geological observations we have from the surface of the Earth, but this is information coming from much deeper down in the Earth's mantle. And it's really satisfying to see that the numbers sort of match up. So that's lithospheric diamonds. We were talking about diamonds that form as deep as maybe 200 kilometers. Now I want to talk a little bit about super deep diamonds, ones that form much, much deeper in the Earth. And that's what these diamonds are. So these are two journal articles that I published. On the left, this is 2016, and on the right, this is 2018. And these were published in Science and Nature. Again, these are big journals. And this was a story about type 2A diamonds on the left and type 2B diamonds on the right. And what we've learned is that both of these major kinds of diamonds that make up some of the biggest and best diamonds that we know of, they actually form some of the deepest diamonds that we know of. And these are super deep diamonds. So let's take a look at type 2B diamonds in particular. So these are diamonds that are characterized by the presence of boron in the crystal structure. And it's not very much. So ppm stands for parts per million. So quite often type 2B diamonds could have 0.1 or maybe even upwards of 1 part per million boron. So most of the diamond crystal is still carbon, but it still has a couple boron atoms here and there. And that's enough to give it this color. So the Hope diamond is a perfect example of a type 2B diamond. And this is, from a geological perspective, very unusual because there's lots and lots of boron at the surface of the Earth, but down deep in the mantle where diamonds grow, there's very little boron. So for many years, people have wondered where this boron comes from and how it fits into this story of diamond growth. So I was lucky in the past few years to be able to study type 2B diamonds and the inclusions within them. And this is the reason why I'm at GIA, is because this is a place where diamonds are sort of coming from all over the world, and you can study diamonds like type 2B diamonds that would otherwise be almost impossible to study at a university or at another research institute. So I'm really fortunate to be at a place where these diamonds are coming through in a sort of steady stream for grading. Now, we talked about these inclusions already, looking at these two rock types, eclogite and peridotite, and the minerals that are trapped inside these diamonds, the olivine and the garnet. Well, I'd like to introduce you to this diagram here. So this is showing these same two rocks, peridotite on the left and basalt or eclogite on the right. And what we can see in this diagram is the minerals that make them up as a function of depth in the Earth. So on the vertical scale is depth. So we're going from 200 down to 800 kilometers, all the way down to 1,000 kilometers. So those earlier examples of mineral inclusions we looked at, we had olivine and we had garnet, but those are things that we find at shallower depths. And if you take that rock, that package of rock, and move it down all the way down to 400 or 600 or 800 kilometers deep in the Earth, some of the minerals in it break down. They're not stable at higher pressures and temperatures. So some minerals break down and some new minerals form within those rocks. And so, for instance, olivine isn't stable anymore once you go below 400 kilometers and you start forming new minerals. And when these new minerals are trapped inside diamonds, they're like a marker for the depth of diamond formation. So when I studied type 2B diamonds, instead of finding things like olivines and garnets, I was finding things like this yellow phase here. So it's not important what that is, but it's a yellow phase in this diagram called calcium perovskite, and it only forms in the mantle transition zone or deeper, so deeper than about 300 or 400 kilometers in the earth. I also started finding inclusions of this orange phase here. This is called Bridgemanite, and again, this is something that only forms at extreme depths in the earth. And there are a few more examples of inclusions that I found that are things you only find at very high pressures. And together, these things tell us that type 2B diamonds must have formed at extreme depths, and there's no way that they could have trapped these inclusions if they had formed at shallower depths. So it's like this marker for their depth. These are just some more examples of what these inclusions look like. And in some cases, they're very complicated looking, and sort of understanding exactly how they formed can be a bit of a task. It's not so simple, but it can be a few days' work to understand what these inclusions are and what they mean. So here's an example of a type 2B diamond that I studied, and you can see some of these inclusions within them. So this is an example of one of these diamonds that I was sort of analyzing and trying to understand what the mineral inclusions are. So in that last slide, I showed you the mineral inclusions that we found, and now I can show you what that means. So this little diagram here, this is the same diagram we were looking at before, and I showed you all those different mineral inclusions that we found, and they're things that can only have formed very deep in the earth. So in this diagram here, I've shown these blue diamond symbols standing for type 2B diamonds, and they're forming at depths of maybe 660 or maybe even as deep as 800 kilometers in the earth. And the other thing that I want to mention is, remember this rock type on the right here, this is the eclogite, and this is something that represents ocean crust. And there are a few other observations that support this, but I won't talk about them here. But the idea is that the inclusions we see tell us not only that type 2B diamonds are super deep, but they also tell us that their formation involves ocean crust, or this ocean plate that's been subducted deep down into the earth. And remember before I mentioned boron, I said boron is kind of unusual to find in these diamonds because there shouldn't be much boron deep in the earth. Well, the idea we have now is that maybe this boron that we see in these diamonds has actually been carried down into the earth by this subducting plate. And the boron might have originally been at the surface of the earth, and it's been carried down by these rocks that have physically moved through space, being subducted down to this very deep environment where the diamonds themselves have grown. So this is sort of a little snippet of what I see when I see diamonds. So here's an image I took of these beautiful diamonds, and I appreciate them as gemstones, but I also appreciate them as these sort of truly exotic samples of the earth that are so scientifically valuable. So I just want to conclude by saying some summary points here. We said there are multiple different ways natural diamond can form, and from studying their inclusions and their crystal chemistry, diamonds are actually some of the most scientifically valuable samples of our planet. And we saw things like they have this record of plate tectonics and recycling of material back into the earth through that process of subduction. And some of the best and biggest diamonds out there, like the Hope diamond or this type 2B diamond here, some of these diamonds, world-class diamonds, are actually super deep diamonds. They form way deeper in the earth than we ever imagined. And this is something we've just learned within the past 4 years. And I think that we'll continue to learn more because every diamond tells a story. I love looking down the microscope and peering inside a diamond and seeing if there's anything in there that tells a story that you can interpret and learn from. So that's all I wanted to talk about today. I think we might have time for some questions now, and I'd be happy to answer anything you might have.
All right, Evan, thank you very much. I cannot see for now any questions. יש למישהו איזושהי שאלה שהוא ירצה לשאול את המרצה? אני לא רואה כרגע איזשהם שאלות. All right, I cannot see any questions right now in the chat, but I would really want to thank you, Evan. It was really a fascinating lecture and presentation, a lot of information, and I really will ask you maybe in the future also if we can host you here in other lectures from the GAA. Very, very interesting for us. Somebody is asking if type 2B is blue.
Usually, yes. But I should say that some type 2B diamonds where we can measure boron in them, they don't have enough boron to make them blue. And some blue diamonds are not necessarily type 2B. For instance, it's possible to take a type 2A diamond and irradiate it and turn it blue. But the classical, I think most people's classical idea of a blue diamond would correspond to a type 2B diamond.
All right. Thank you for the answer. And this lecture is recorded and everyone can see it also later. And I will move to Hebrew. תודה רבה לכל מי שהשתתף. אנחנו מודים למרצה שלנו, לדוקטור אבן, ואנחנו נשמח לארח אתכם כאן בהרצאות נוספות. גם בהמשך, כמובן נפרסם, אנחנו נשתדל לפחות אחת לשבוע לעלות הרצאה מעניינת לציבור היהלומנים, וכמובן נעדכן אתכם כמובן בהמשך ההנחיות לגבי הסגר. כולנו מקווים שנוכל לחזור לעבודה פעילה יותר כבר בעתיד הקרוב. אז תודה רבה. Thank you, Dr. Evan, and see you next time.
Thank you very much. It was my pleasure to be with you today.
Thank you very much.